Good afternoon. So let us continue our lesson with mathematical induction. So we introduced the notion of the mathematical induction as a very strong way to prove the statements regarding natural numbers. Yes. So I told you that assume that n is a natural number, and then Pn is a statement stating something regarding that natural number, and you want to prove that that is true. Yes. Of course, you have different ways to do that, but one very strong method is actually mathematical induction. So I want you to repeat that again. This only works if you are working to prove a statement regarding natural numbers. Okay. And then what you are supposed to do, you show that the first one is the induction base. So what you do, you replace n in your statement with 1 and read the statement again and confirm that the statement is true for that n equals to 1, if that is the case. If that's not the case, then it means that this is a false statement, so you have to leave it. But if it is going to be true, it has to be true for 1 as well. So you check this manually. And the second part, you take an arbitrary k from the set of natural numbers, and you yourself assume that p of k is true. There is no guarantee that p of k is true. You assume that p of k is true and try to convince yourself that the truth of p of k implies the truth of the next step, k plus 1. Yes, so I want you to understand there is no guarantee that p of k is true. I myself assume that p of k is true for a given number k in a set of natural numbers. I will try to conclude that the next step is true. Then these two together will imply that p of n is true for all natural numbers. And intuitively it is very clear, yes? When you say that this is true for n, for 1, and you tell me that if this is true for k, definitely it is true for the next step, k plus 1, then if you put these together, you will see that, okay, p of 1 is true. And now this tells me that if p of a number is true, p of the next number is also true. P of 1 is true, so I can conclude p of 2 is true. Now p of 2 is true, I can go to the next step, p of 3 is true. And now p of 3 is true, I can go to the next step, p of 4 is true. So then eventually you realize that p is true for all natural numbers n. Okay? So if this is true, and this is the truth of p of k implies the truth of p of k plus 1, then I can say that p of n is true for all n in n. So that was the idea of mathematical induction, and then last time I gave you some examples, and now I want to give other examples. So the point is that I want you to learn that mathematical induction can be used in different areas of mathematics. Whenever you have a statement regarding a natural number and you want to prove it, it doesn't matter if it is in algebra, it doesn't matter if it is in number theory, it doesn't matter if it is in geometry or whatever. If it is related to the natural number, one way to think about the proof that statement is to think about induction. Yes? So now I want to change the type of problems that we have considered so far to the new problems that is in the book as well. So example, let n be a natural number. Use mathematical induction to prove the following equalities. So I think it is good to start with a very, very simple case, and then you are familiar with this. 1 plus 2 plus 3 up to some number n, we want to show that this is equal to that. Okay. Of course, you know this formula is true, but not from mathematical induction. If you remember, this is a arithmetic progression, and that is Sn, and we actually discovered that this sum is equal to this one. And now we want to use mathematical induction to prove the same statement. And then, of course, there is a weakness of mathematical induction. Do you remember, in the previous lesson, we didn't know the formula. We discovered that. Yes, but mathematical induction is not good for these kinds of problems. You should have the problem in its entirety and then show that this is indeed true. So if I don't have the formula on the right hand side, mathematical induction will not help me to do that because I don't have a statement. A statement means a declarative sentence. This tells me 1 plus 2 plus up to n is equal to this full stop. So that's a declarative sentence, that's a statement, yes? But if I don't have that on the right hand side, I do not have a statement, I have just an expression. So this is the weakness of induction. But somehow, even if you don't have this formula, might be by just taking care of some particular cases, you can find the pattern, and using that pattern you might be able to guess, and then after guess you can use mathematical induction to prove it rigorously. Yes, but anyway, I want you to know that if you don't have the right hand side, mathematical induction is not that useful. Okay? Okay, now that we have the right hand side, what we do, what is your statement? The statement is this. Pn is telling you this. 1 plus 2 plus 3 plus up to n is equal to n times n plus 1 divided by 2. This is my statement. I don't know if this is true or false. I want to prove it using mathematical induction. The base of induction tells you that check this manually for 1. So it means that you have to write this statement for n equals to 1. Okay? So what does this mean? It means that you start from 1 and add 1 unit at a time until you reach to n. Yes? But now n is 1. What does it mean? I do the same thing, I write 1, and then I have to continue to reach to n, which is 1. So it means that I stop here. Yes? And then ask this question. Yes, let me take the question mark. And then instead of n, I put 1 as well. Okay, this is a statement. It might be true or false. In this case, it is true. Yes? So then you need to write true. Okay, so that is the first part. So I check the formula works for at least n equals to 1. Yes? And then I need to assume that P of k is true. Yes? So it means that write the statement for k instead of n, but that's an easy task. Just replace every n with k. Yeah, so it becomes what? 1 plus 2 plus 3 up to k equals to k times k plus 1 divided by 2. Yes? This, if I ask you, is it true or false? I don't know. This is assumed to be true. Be careful about this. Because for some people, it seems a little bit strange, yes? You see, I am asking you to prove this formula, and I am writing the same formula, changing n to k, and I am asking you to assume to be true. If that's true, so that's also true, yes? I want you to understand the logic. This is not a circular argument at all. I assume that this is true. Even it might be even false. I don't know. But I'm assuming that this is true. I want to show it is possible to go from this step to the next step, independent of this is really true or false. I'm assuming that this is true. But okay, it means that now I have to write the same statement for k plus 1. What does it mean? It means that you need to, by the way, interpret it in this way. When I give you a number, you start from 1, adding 1 unit at a time until you reach to the number given. The number given is k plus 1. If I want to repeat this process, I have to start with 1, add 1 unit at a time, continue until I reach to k plus 1. Okay, so I reach to k plus 1, and then I replace k with k plus 1 here as well. But if you do it in your head, k plus 1 becomes k plus 2, and then divided by 2. Yes, that is what I want to show. Yes, and based on experience, you will see why. For these kinds of problems, let me put a pair of brackets to show that this is the last step. And if this is k plus 1, it is clear if I continue in this way, what would be the previous step? It would be k. And this is why I recommend you to, for these kinds of problems, including these dots, it's always better to write the previous step as well. And now this is to be proven. Yes? So, but look, if I ask you to prove this, you are empty-handed. But now if you want to prove this, you are no longer empty-handed. You have something in your hand to use to prove it. It seems like that you are using the problem itself to prove it, but if you understand the logic, it is not circular at all. It's a really valid argument. Yes? Okay, then what to do? I want to prove this statement is true. This is equality, yes? So it means that usually if I want to prove equalities, I start from the left-hand side or a more involved side and try to simplify it to reach to the other side. So my goal is to prove this, so I would write the left-hand side. The left-hand side, let me repeat it here, 1 plus 2 plus 3, it goes up to k, and it goes to the next one. This is my left-hand side. Okay, I want to show this expression is equal to that expression. But I have something in my hand now. I know that from 1 to k, if I add them, it becomes this. So then the problem is simple, yes? So from here to here, I know the result based on my assumption. From 1 to k, which is the hard part of this sum, yes, because the dots appear here exactly. So instead of that, I can write k times k plus 1 divided by 2 plus k plus 1. Yes? Okay, and then I have to simplify and convince myself that this is indeed equal to the right-hand side. But this is a very simple algebra. So what I have to do, I have to make the common denominator. For example, I take the common denominator to be 2, then it becomes k times k plus 1, and then I have plus 2 times that one. And then one more step is left to see that k plus 1 appears as a common factor, so I can pull it out, yes? Then it becomes k plus 1. And then what is left from the first one? K is left, plus from the last one, 2 is left. And then divided by 2. And then you see that you exactly get the right-hand side. So this means that the left-hand side is equal to the right-hand side. Yes? But look, this doesn't mean this is true or false. This part only. If I do not do the first part, these parts only tell you that if this is true, which is not guaranteed, yes? If this is true, then this is true. What I have shown is this. I don't know if this is true or false. I don't know, but I'm telling you that if this is true, I can show you that this is also true. But that is your responsibility if this is true or false. I don't care. What I care is that if this is true, this is also true. So it doesn't work if you don't check P1 manually. So I want you to understand, this is extremely important to check P1. Yes? Because if you don't P1, you don't have the first step to actually go up. So this tells you that from stair number k, you can go to stair number k plus 1. But it doesn't tell you more than that. If you want to start climbing up the stairs, you have to start from somewhere. Yes? This tells you that if you can put your, your foot on the first one, then I can show you that you can go to the second one. Now that you are on the second one, I can show you that you can go to the third one, etc. Is that clear? So, today we want to talk a little bit about these kinds of formulas. Mainly, mathematical induction are very good if you want to prove the formulas. Okay, so let me increase the level of that a little bit. So here, for example, if I give you number 2 here, 1 to the power of 2 plus 2 to the power of 2 plus 3 to the power of 2 and then plus n to the power of 2. If I do not give you the right hand side, then you have a little bit of problem solving this problem that I'm supposed to write using mathematical induction, because you don't have the right hand side. And I don't think that is hard. I don't know. Do you think that you can guess the pattern? So this is not geometric, because you know that the first number is 1, the second number is 4, the next number is 9, and then it is not geometrical and it is not arithmetic. Yes? So we don't have any particular formula for that. Okay. Of course, the person who designed the question first, probably they were able to find the right hand side without mathematical induction. But now I want to see that this is not that easy. Can you guess the pattern? The pattern for this one wasn't that hard if you just calculate it for several numbers. But can you find the pattern for this? For example, if n is equal to 1, then I will have 1 to power 2, which is 1. If I have 2, then it becomes 1 to power 2 plus 2 to power 2, which is 5. Yes? And if I have 3, I have 1 to the power of 2, 2 to the power of 2, 3 to the power of 2, which is 5 plus 9 is 14. And the next one is what? What is that? 30. I don't know. Can you see a formula that generates these numbers one after the other? It's not that easy, I think. It's not complicated, but it is not probably that easy to guess a formula that generates these numbers one after the other. So that's why I'm saying that. Yes?
Square numbers.
No. That the sum of a square. No, this is not a squares. I am asking you find a formula that generate these numbers. So the point is that I'm not expecting you to guess this, but I'm expecting you that this is the weakness of mathematical induction. So if you don't have the right hand side, there is nothing to prove. You know, you have to have the right hand side. So what is the formula? I write the formula. Okay. So then n times n plus 1 times 2n plus 1 divided by 6. So that's the answer. You can check that this is true for these. For example, if I put n equals to 1, 1 times 2 is 2, times 3 is 6, 6 divided by 6 is 1. And if I put 2, 2 times 3 is 6 is cancelled, 2 times 2, 4 plus 1 is 5. And then if I put 3, for example, 3 times 4 is 12, it is 2, and then this is 7, it's 14, that's 14, and then you can calculate these things, yes? So, that was not easy, that's my point. If you don't have the right-hand side, mathematical induction is not that useful, yes? Because finding the pattern is in the first place very hard. Okay, but now that you have it, you should be able to prove it. And then I would say it's not that hard at all. So what is the statement? So let us, so this is your Pn. So let me not write it. This is your Pn. Okay, and I check it for 1. So what is for 1? This becomes 1 to the 2, and then you stop. Because you are supposed to start from 1 and continue this pattern until you reach to the n to the power of 2, but n is 1, so you stop there. But on the right hand side, you write 1 instead of n, 1 plus 1, 2 times 1 plus 1 divided by 6. Is it true or false? It's just simple calculation, yes? 3 times 2, 6 times 1, 6 divided by 6, 1. 1 to the power of 2 is 1. So this is actually equivalent to saying 1 is equal to 1, which is of course true. And again, you assume that k is a natural number, and you assume that this is true for k. 1 squared plus 2 squared plus 3 squared up to I reach to k squared is equal to k times k plus 1 times 2k plus 1 divided by 6. And then, so this is assumed to be true, so let me write it here. And then we are supposed to show that this is true for the next number. So I have to show that 1 to the power of 2, 2 to the power of 2, 3 to the power of 2, if I continue this pattern until I reach to this number, which becomes k plus 1 to the power of 2, is supposed to be equal to this expression if k is being replaced by k plus 1. So let us do some calculations in our head. So this becomes k plus 1, this becomes k plus 2, but then remember, I change k to k plus 1, so don't get confused. So it becomes 2k plus 2 plus 1, which is 2k plus 3, divided by 6. And then I told you that by experience you know that it is better to write the previous step, which of course is k squared. So this is to be proven, yes? Okay, I'll wait for you a little bit to do it. Okay. Okay, so what happened? I don't think it's hard, is it? So you will start from the left-hand side. I would prefer. So for this time, you are getting experience now. For these kinds of problems using mathematical induction, it's better to start from the left-hand side of what are supposed to be proven, and then reach to the right-hand side using your assumption. Yes. So I would start from the left-hand side here. Let me write it here. So the left-hand side becomes equal to. So you don't need to repeat it, but let me just repeat it so that you can have it in front of your eyes. So this is the left-hand side that I have. And I want to convince myself that this sum is equal to this. But the hard part of it is actually known, is assumed to be true. So I can replace this with that one. Yes? So what happens? So from here to here, I know the answer is this. So then it becomes k times k plus 1 times 2k plus 1, and then divided by 6, and then I will have k plus 1 squared. Okay, then the rest of it is just probably simple algebra. So you have to manipulate it algebraically in a way that you can get this. For example, you see that you have one fraction involved, but I have one fraction and expression. So this will motivate you to take the common denominator, yes? So what will happen? The common denominator is actually 6, and then nothing will change for the first fraction. And then plus 6 times the other one. Yes? So this is so far. And then you see that what I want on the right-hand side is fully factorized. So then it motivates me to factor k plus 1 out from both of them, yes? So then I will take k plus 1. And then what is left? K and 2k plus 1 are left. So k times 2k plus 1. And then plus 6 times k plus 1. Then divided by 6. Okay, let us simplify this a little bit. So then it becomes equal to what? Then it becomes equal to k plus 1. I multiply that k inside, it becomes 2k squared. Then it becomes k. Let us do it in our head. Then 6k becomes 7k. And then finally 6, yes? And then divided by 6. Yes? So we have this one. And then it is not finished. Of course, I want to reach to k plus 1. We have it, so it's good. I have 6 in the denominator. But instead of these two factors, I have this one, and I can teach you a little bit of cheating. So if you have done your calculations correct, you really don't need to be worried about factorizing this. It is already factorized in that form. So you can write it like that, yes? But I can, yes? So I can write it as k plus, what? K plus 2, 2k plus 3. Divided by 6. And then you can say that k plus 2, because factorization is usually harder, but expansion is easier. And then if you trust your calculations up to here, you can do a little bit of cheating. So you just write that and then convince me that this is indeed the case by multiplying it in, yes? 2k squared, 3k, and then 4k and then 6. And this is exactly that expression. So it's convinced that this expression is indeed equal to this. So I can take it off and replace it with that expression. Now this is equal to the right hand side. Yes? Is that okay? Okay, before continuing, let me just give you one example. So, for example, if I ask you to prove this, okay, so let us see what happens. I assume that this is true for k. So it means that, just please listen, I want you to understand something here. So I assume that this is, I want to prove this. I assume that this is true for k. And I show that this is true for k plus 1. Yes? Yes? But of course I told you that based on experience you know that it's better to write the previous one. Assume to be true to be proven, yes? Let us see if it works or not. I start from the left hand side and then what I have from here to here, according to assumption, is this one. And then of course I have this k plus 1. Okay, and now let us take the common denominator. So this becomes k squared plus k plus 2 plus 2k plus 2. Agree? So then it becomes k squared plus 3k plus 4 divided by 2. But hopefully this is the same. Let us check. So here I can write it as k squared plus 2k plus 1. So remember, k squared is used, 2k is used, 1k is left. So I use it now. So 3k's are used. 1 is used here. I will use here and here. Yes? And then what happens? It becomes k plus 1 squared plus k plus 1 plus 2 divided by 2, and that's exactly equal to the right hand side. So let me repeat. I wrote a formula here for you and I asked to prove it using mathematical induction. So I assume that this is true for k. I want to show that this is true for k plus 1, and I succeeded that. So, but this is the wrong formula, yes, because we just right now proved that n times n plus 1 divided by 2 is the correct formula. This is n times n plus 1, but an extra 2 we have there. Yes? What is the problem with this?
It doesn't make it work for me.
Yes? Anyone, yes.
We didn't do the P of 1.
Yeah, so you see it's super important. If you don't care about, so this step I want you to see, you see it was a wrong statement in the beginning. But I assume that to be true. This I was able to show that if you say this is true, that is your responsibility. I can show you that the next one is also true. If you say this is true, I didn't check that. If you say so, I showed that based on this, I can go to the next step. So you see it works here again. The only weakness about this method is that I didn't use the, check the P1. And if you check P1, you realize this is wrong. Because if I put 1 here, the left-hand side becomes 1, the right-hand side becomes 4 over 2, which is 2. But except for that, you see it worked. Assuming that P is true for K, I was able to show that this is true for the next step, but this one was false because P1 was not checked. So be careful, you have to check P1, it's extremely important. And if you don't care, by the way, about these things, there is a very nice thing that people can prove that everyone is bald. They say that, okay, let us check P1. If you have one hair strand on your head, you are called bald. And then if you have K hair strands on your head and you are still called a bald person. If you have one more, you are still bald, yes? So then you can prove that everyone is bald. What is the problem? Yes? So what is the problem of this argument? Okay, what is the problem? Is this a problem with mathematical induction? Because apparently, even me, I am not bald. Yes, not bald. Yes, yeah. So then, apparently, we have a lot of counterexamples even in this classroom. So what's the problem of this argument? Mathematical induction using apparently using mathematical induction. Yes. Yes.
The first statement is false. Because if you have one strand of hair on your head, you're not actually bald.
Okay, so that's probably correct. So the problem is that you have to define what is the meaning of bald. How many hair strands do you need to be a bald person and pass this threshold? Yes. so I mean that you have to be careful. P1 is extremely important, and this is a very good example because it shows that this process can work even based on a false statement. Yes. I start with a statement, responsibility of the truth of that is yours, but if you say this is true, what I can do, I show that the next one is also true. Yes, do you understand that? So this is very important that you check P of 1. Okay, now I will write something on the board here, and I want you to prove that. This becomes a little bit harder, but that is not my goal. So I want you to prove number 3, 1 to the power of 3, who cares? Let us increase the powers, yes? And then 2 to the power of 3, and then 3 to the power of 3, and then we continue until n to the power of 3. Can you guess a formula for this?
No. Divide by 12.
Can you guess the pattern how it will go? For example, for 1 cube is 1. For 2, 1 cubed plus 2 cubed is how much? Is 9. And then there is something going on. Interesting. This is probably easy, not that hard to guess. Can you guess what is the pattern? Let us check. 1 to the power of 3 is 1. 1 to the power of 3 plus 2 to the power of 3 is 9. And then 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 is 36. Yes? And then 1 to the power of 3 plus 2 to the power of 3 plus 3 to the power of 3 plus 4 to the power of 3 is 100. Yes? And now probably you can see the pattern. It's easier than the previous one, even though the power is higher. You see the pattern. At least you can see. Do you remember Martin told that these are complete squares? Yes. Here now they are all complete squares. But this is complete square of 1. This is complete square of 3. This is complete square of 6. And then this complete square of 10. What would be the next? Don't cheat by calculating. What is the next? Okay, cheat. Okay, cheat, yes. What's the next?
15 to the power of 2.
15 to the 225. So that would be 225. And that's clear because I have to add 5 to the 3. 5 to the 3 is 125. Added to this, that is the cheating. But not cheating means guessing. Okay? Can you guess the next one? So what was your pattern? How did you come up with this answer?
The first one is just 1 to the power of 2. The second one, you add 2.
So yeah, this is the power of 1. This is power of 3. This is power of 6. This is power of 10. And how did you come with power of 15?
Between 1 and 3 there's 2.
2.
And then between 3 and 6
It's
there's
3.
3.
And that's 4.
So
And then probably that should be 5.
I was supposed to know.
Yes? So that was the pattern. So the pattern, this one is easier. Do you agree with me? Now, you will be actually excited now. I want to write a formula. You should be excited. If no, that's your problem. Okay, so this is this one. Okay.
Oh my god.
Yeah. Are you surprised? No. It is really counterintuitive. Why is that? Why it is counterintuitive?
Because why is it squared? Why is it not cubed?
No, no, more than that. More than that. Because if you should be actually have a heart attack now. So why is that? This number is famous. What is that number?
It's the sum of the...
And the sum from 1 to n. It means that if you add from 1 to n and square it, it becomes the sum of cubes. It's really counterintuitive, isn't it? And this is true. So it means that we are proving this ridiculous statement apparently, yes? So we have 1, 2 to the power of 3 and then n to the power of 3 is 1 plus 2 up to n to power 2. So if you do, so that's very, very interesting. If you write it in this way, it's really counterintuitive. Might be you are not able to guess, but this is true. Yes, and we want to prove it. If we use mathematical induction, this is why mathematical induction is also powerful here. Because if I tell you right now, you will not probably buy it, because you say that, okay, you check a few number of steps, might be this will deviate, especially because of this very strange thing. But then I use mathematical induction to say, no, mathematical induction shows that this is true forever. So this means that we have to admit that there is no deviation from this general pattern anymore. Okay, I wanted to prove it using mathematical induction. But this was very, very interesting for me when I saw it for the first time. Okay, I will pause recording. And then you can think a little bit about it. Okay, I will also write one more there. If you finish this one, don't waste your time. Go to the next one, okay? Yeah, this one, I think, because I changed the problem from what was written here, I hope that I haven't made any mistakes. So, 1 times 3 plus 2 times 3 to the power of 2 plus 3 times 3 to the power of 3 plus 4 times 3 to the power of 4, and etc., etc. You want to see that if you add them, it becomes that. Yes? Okay, what happened for this one? This one, you tell me, is it true or false? If it is true, prove it by mathematical induction, and if it is false, tell me why. Okay? But this is totally true. We are sure about that. And I don't think it's very hard for us to prove it, unless you have a little bit problem of factorizing these polynomials at the end. And by the way, in the exam, you really don't have to factorize. You can simplify it up to some point, and then go to the right-hand side, simplify that one as well, and compare that they are the same thing. If you are not very good in factorizing, you don't have to do that. Okay? So let me solve this problem for you, and if you are sure that you know that, you don't need to listen to me, you can go there and see that if this is true or false. Okay, here, P of n is this expression, so P of 1 is 1 to the power of 3 equals to 1 times 1 plus 1 divided by 2 to the power of 2. This is true. Yes? 1 times 2 divided by 2 is 1. 1 to power 2 is equal to 1 to power 3. That's true. Now we assume that K is true. So we assume that 1 to the power of 3 plus 2 to the power of 3 up to 3 to the power of 3 up to n to power 3. Sorry. K to power 3 is equal to K times K plus 1 divided by 2 to the power of 3. We assume that this is true. And now we want to show that if this is true, the next step is definitely true.
Baba,
Yes?
the power of 2.
Oh, okay, thank you. Thank you. So, sorry, K plus 1 to power of 3. I should show that this is equal to K plus 1 becomes K plus 1, K plus 2 divided by 2 squared. to be proven, yes? And then you have experience by this. So I start from the left hand side of what I want to show. But from here to here, I don't have any problems with, because I have assumed that this is equal to that. So then it becomes k plus 1 to the power of 2, divided by 2 to the power of 2, plus this expression. Yes? And then I have to simplify and convince myself this is equal to this expression. What we can do, for the time being, we can square it. So this becomes k squared, k plus 1 squared, divided by 4. And then I have plus k plus 1 to the power of 3. At least I can see it's one expression, so let us take the common denominator. So it becomes k squared, k plus 1 squared, and then I have 4 times k plus 1 cubed. Okay, and then you see that I have to factorize it in somehow because I need this. That is my recommendation. If you find factorization a little bit hard, you can expand this. You can expand that and compare that these two results are the same. But here it's not that hard because k plus 1 squared is in common. So at least you can see this step easily. You can take this one out. And then what is left from the first term is k squared. What is left is 4 times. By the way, it was very, very simple if you want to factorize right now. Yes? I hope that every one of you could see that. Because if I multiply 4 in, so it becomes k plus 1 squared. If I multiply 4 in, it becomes k squared plus 4k plus 4. This is a very standard factorization. This is a squaring pattern, yes? And divided by 4, so this means that this becomes k plus 1 to the power 2. Instead of this expression, I can write k plus 2 to the power 2 divided by 4. And of course, you can write it as one single power of 2. K plus 1, k plus 2, and then divided by 2. And that's exactly equal to the right-hand side. Yes? Okay, so now you have enough experience about these identities containing these dots, and I want to give you that one. Now, for that one, I ask you this question. Is it true or false? If it is false, why? If it is true, prove it. Okay? So, I don't know, if you want, I can give you a little bit more time. First, think if it's true or false. If it is false, why? If it is true, prove it. Okay. So in the book, they usually use sigma symbol. For example, for this one, they haven't written it down in this form. They have written it down in this form. Sigma k to the power of 3. I don't know. K goes from 1 to power n to up to n. You are supposed to show this. Yes. But instead of writing this sum, they have written it as a sigma form. Yes, do you have any problems with sigma? Okay, so that's the only difference. I prefer to write them in a full form that you can see, not distracted by sigma symbol. Okay, can you tell me this one, is it true or false? Okay, might be it is hard to evaluate, but what is P1? If P1, P of 1 is true, then might be I have a chance that this is true. If P1, P of 1 is false, then I don't continue. It is false. Now I am asking you, if this is my statement, P of 1 is true or false? You should be able to say something. P of 1 is true or false? Because usually you see that P of 1, checking P of 1 is simple, but now I make it a little bit harder. Is P of 1 true or false?
False.
Yes? Why?
Because P1, if I calculated right.
So if you put 1 there, what will happen? Did you calculate?
Yeah, 30.4.
So if you put 1 here, 5, 3 to the power of 3, yes?
Yeah.
27 times 5, 135. This one is 136. 25, 9 is 34. 34, it's 112, I think. No, 102, yes? Let me double check. I put n equals to 1 here, so it is 3 over 4. And then if I put 1 here, it becomes 5. And then I multiply it by 27. No, I made a mistake. Then plus 1, yes? 5 times 27 is 135, 136. And I divide that by 4, it's 24 and 9, 34. So that's correct. It's 102. Okay, but what is the left-hand side?
It says 3.
3. So false or true?
It's false.
False or, false or true?
False.
False or true?
False.
Everyone.
False.
The right-hand side is 102, the left-hand side is 3. False or true?
False.
False.
Varför säger du så mycket mer? Do you wanna trick?
So why don't you dare to speak?
False.
Yeah.
You should go up to n plus
Yes,
2.
but that is true. This is intentionally I made it like this because you usually take it for granted P of 1 is the first term.
Maybe.
And then you are telling that, okay, Babak is crazy explaining so much. Yes? No. The reason is that I told you that, if you remember, I didn't tell you put 1. I told you that you take 1 and then you take k, you have to start from 1 up to the kth step. That is the meaning of k. Now when I say put 1, if you give me n, I will start from this, I will not stop at n. I will stop when I reach to n plus 2. Yes? Now that you are giving me n equals to 1, not 1 doesn't mean the first term. It means that you have to start from the first term, continue, so that you reach to that number n. Yes? So you see, when I put n equals to 1, what will happen here? It doesn't give me the first term. Yes? If I put 1 here, it becomes 3 times 3 to the power of 3. It gives me this term. So when I say that calculate P of 1, the right-hand side is 102, according to that calculation. The left-hand side should be this. Don't take the first one. If you take the first one, that is wrong, and you will get this impression that this is a false statement. But let us calculate now. Hopefully I haven't done any mistakes, otherwise I will spoil the enjoyment of this one. Yes? So 3, and this is 18, and this is how much?
81.
Oops. Yeah, that's correct. So P1 is true. So be careful. That was the only point. I changed the problem a little bit from the one that I had here to make sure that you understand what is the meaning of P of 1. So P of 1 doesn't necessarily mean the first term. It means that you have to start from the first term as usual, but continue until you reach to the level that you need. When I put n equals to 1, the last term is the third term. So when I put n equals to 1, I have to write from the first term up to that level. This is the meaning of P of 1. Yes? And I think the rest of it isn't that hard. So continue. So P of 1 is true. The left-hand side is 102. The right-hand side is also 102. Now we assume that P of k is true. We want to show that P of k plus 1 is also true. Yes? So this means that I have 1 times 3 plus 2 times 3 to the 2 plus 3 times 3 to the power of 3 up to k plus 2 times 3 to the power of k plus 2 is equal to this. Okay, and then we want to show that this is also true. Yes, I replace k with k plus 1 everywhere, but when I replace k with k plus 1, it becomes 2k plus 2, so this is why I have written 5. That is also k plus 2. This one is assumed to be true. We want to show that the next one is also true. Okay, I went a little bit for you. Okay, could you solve it? Okay, let me solve this one as well, then you are done here. Okay, so if I want to do that, I will start from this side, the left-hand side of this expression. But up from here, up to here, is that expression. So it is 3 over 4 times 2k plus 3 times 3 to the power of k plus 2 plus 1. From here up to here, this is my assumption, I can use it. Then I have this extra term left, which is plus k plus 3 times 3 to the power of k plus 3. Okay, any idea what to do now? Because I want to simplify this expression and convince myself that this is equal to the right-hand side. Do you have any idea how to do it? Any ideas? It's simple. No, the idea is simple. Might be the algebra becomes complicated. I don't know and I don't care. Okay? So the point is that what I need on the right-hand side, I need a factor of 3 over 4 for the whole expression. I don't have it. I have only 3 over 4 for the first bit, not for the second one. But what I do, I can factor it out. Yes? I factor this out. Okay, now I want to ask you. 3 over 4, I factored this out, so I repeated this one. But apparently there is no 3 over 4 here. But I am insisting to pull it out. Then can you tell me what should I write in front? What? 4 over 3 and the rest of it, yes? K plus 3 to the power of k plus 3. At least this is valid. And this is towards the goal. Because I see I have my factor here. For the whole expression, not just for one part of it. And if the question is correct, it should work. So you don't worry about that. So then what happens? Let us simplify it. So I keep this 3 over 4. I repeat this for the time being. And then you have to find a way, yes? And I see that I need my 1 here. So I don't mess with it, yes? I need my 1, so let us put it at the end. This 1 is needed. But this 3 will cancel one of these exponents. So it becomes what? 4k plus 3. Instead of 3 to the power of k plus 3, I will have 3 to the power of k plus 2. And then everything becomes clear. Now I have my 3 to the power of k plus 2. Of course, I don't need it right now. But anyway, I have to factor this out. So this becomes 3 over 4. Don't get disappointed, yes? So this becomes 2 to the 2k plus 3. And then I am factoring this part out. It is 4k plus 12 left. Yes, I am factoring this out. And then I have plus 1 there. Yes. I factor this out. This is left here. This is left. I multiplied 4 inside. Yes. everything looks like the right hand side except for this factor, but that factor is also working, yes? Why is that? Because this is 6k plus 15. Yes? Now I factor a 3 out, it becomes 2k plus 5, which I need, and that 3 that I pull out, I will put it here, and then it becomes k plus 3. Yes? So you see, you have to think what to do efficiently. So then it becomes 2k plus 5, and then I have 3 to the power of k plus 3 plus 1. And that's exactly the right answer. Yes? I need one more session for finalizing the induction, so we will do it on Monday. And on Thursday you will get some time to practice, and on the next Monday you will have exam. Okay, so that's fair enough. And I have a news to share, so let me stop recording. Yes?